Hi Apes, this is the last screencast for the summer assignment, and it is on population dynamics. We're going to be doing a lab the first week of school on population dynamics and doing some sampling of some populations. So with animal population dynamics, you have a population which is all the same species in the same geographic area. Size is the number of organisms. Your density is the number of organisms per unit area. Okay, so there are 5 antelope in 1 square mile. And then you have your distribution, so the location of individuals within a specific location or a specific area. So with population dynamics, we study the changes in size and composition of these populations. So the growth rate is how fast it's growing, which is your birth and your death. So your natality is your birth rate, your mortality is your death rate, and migration is moving in or out of the population. So distribution is where in an area it is. Okay, so it's determined by the habitat and the resource availability and the amount of territoriality in these animals, or maybe even autotoxicity in plants. And it can be random, uniform, or in clumps. So when things are randomly distributed, each individual is usually independent of each other. And this random distribution isn't super common. Spiders, clams, some trees are randomly distributed. Then you have uniform, and uniform is where organisms are almost evenly spaced. And a lot of this has to do with intra-specific competition. Okay, so that's within the population. So if you look at the picture, the saguaro cacti, they compete for moisture. And so there's only going to be a certain amount of moisture in a certain area. So they need to be spaced out enough so that they don't infringe on each other. However, there are the maximum amount in that certain area for efficiency. So territoriality is sometimes, and autotoxicity, the same issue there. Clump distribution is the one that we most commonly find, and that is where these individuals are clustered together in groups. They can occur around a resource or around shelter or different types of habitat. And this results as from habitat differences, the seasonal changes in weather and the environment, and a lot of reproductive patterns and social behavior, like a school of fish. So your density is number of organisms per unit area. So with solitary animals, usually you have low density populations, and then you have high density populations where they're crowded together. So a lot of colonial animals, rabbits, corals, termites, schools of fish, things like that. You have density independent factors and density dependent factors, which figure out which lead to how many organisms are in a population. So your density dependent is higher population densities are going to have a greater effect. So at higher densities, individuals are going to compete for more resources. They're more easily located by predators and by parasites. They're more vulnerable to infection because they're closer together, and disease. And these are usually biotic factors. Okay, food supply, disease, parasite infestation, competition, predation, stuff like that. You think about it when you're in school. You're in a classroom, somebody sneezes. If you're sitting a couple people away from them, it's fine. You pack more people into that classroom, and there's more of a chance that you're going to get sick because everyone is closer together. Density independent, it doesn't matter how many people are in this area. So it's not dependent on the population's density at all. So your physical or abiotic factors are usually things like this: your temperature, precipitation, humidity, acidity, salinity, and catastrophic events, especially like floods and tsunamis and fires and hurricanes and stuff like that. When you think about it, it doesn't matter if you're sitting in a classroom. It doesn't matter how many people are in that classroom. If a tornado rips through it, whether there are 20 or there are 40, that whole population is going to be affected. Drought, earthquake, and eruption, those are just a couple more. Okay, so population growth, you have the number of individuals added and the number of individuals taken away. Okay, so when we're talking about the Earth, you can only be born into it or die out of it. But when we're talking about something like a country or a population in a certain area, you can also have immigration and emigration. So your births minus your deaths plus your immigration minus your emigration. There's always going to be a positive in front of things that are coming in, like your births and your immigration. There's going to be a negative in front of things that are going out, like your deaths and your emigration. And that's going to figure out how fast your population is growing or shrinking. There are multiple ways that you can rearrange this formula. So if you see it in a different way, it's not wrong. It's just rearranged a bit differently, like you see in your math equations. Exponential growth is often used by colonizing populations. They grow very, very quickly, exponentially. And we call that a J curve because it looks like a J. In natural populations, this rarely continues to increase because something's going to exert pressure on it, and there aren't going to be enough resources for all of those individuals in the population. So here we come to logistic growth, and you can see here as the population grows, the increase, it will slow and it'll stabilize at a level that could be supported by the environment, basically your carrying capacity. So here what you have is there's a bit of a lag, and then during the early phase your population will grow exponentially. So your J curve, then pressure, environmental resistance will exert pressure onto your population. There won't be as much food, there won't be as much water, there won't be as much space because all these individuals are packed together. So what ends up happening is that your population kind of levels out. And then what happens is it'll go up and down and up and down. And usually that has to do with predator-prey relationships and the increase and decrease in different resources depending on the season or the years. So this we call our logistic growth curve. And this, your J curve then turns into an S curve. You see that curve shape there. Okay. R and K selected species are because your K selected species, this dotted line represents your carrying capacity, which is the amount of organisms that an area can support indefinitely. This is your happy medium. So we call these organisms that usually live around here our K selected species. And your R selected species over here, their populations can grow exponentially almost all the time. So your biotic potential is the maximum reproductive potential, and that is symbolized by the letter R. And the density or carrying capacity is your K, so that's how you get your R and K selected species. So your R species, they can increase very quickly. They're your R selected, your opportunistic species. They're generalists. They'll usually adapt to many areas: algae, bacteria, rodents, insects, and most annual plants. So they can live in many climates. They're density independent, usually of mortality. The survivorship curve we're going to look at on the next couple slides. Okay. Usually their population size can fluctuate. They are early reproduction, so it takes them a short amount of time to reproduce. They have a smaller body size. They usually have a shorter gestation time, so they can have more and more babies. They usually have short lifespans as well. Whereas your K-selected species, I like to think of our selected species as rodents, and cockroaches, your roaches, okay? And your K-selected species are totally and completely different. Usually they use their resources more efficiently. They have fewer offsprings, longer lives. They put their energy into nurturing their young. And large mammals, birds of prey, large long-lived plants, elephants, humans, climate, they need specific parameters. These aren't your generalists. These are usually your specialists. They need a certain habitat and environment to live. They're usually density dependent. They're type 1 and 2 for survivorship, which we're going to go into. Their population size usually stays pretty steady. They usually have pretty specialized niches, and they have slower development, larger body size. They have delayed reproduction, so they reproduce later on in life. They don't have very many offspring at a time, and they live longer lives, and they tend to have longer gestation times. And human, the gestation time, the amount of time that they actually carry a baby is 9 months, whereas for an elephant it's I think 22 months, so just under 2 years. And then for your largest animals in the world, like the blue whale, they're 2 years, or they could be a little bit over 2 years. It's crazy. So here are your survivorship curves, and what this is it's you can represent the age structure, and we'll do this when we get into human population dynamics. So this is where the heaviest mortality occurs. So you have the number of survivors in this population versus the age. So when we look at type 3, these are basically your R selected species. That's my crappy R. And what happens is when you take a look at like fish and oysters and barnacles, you have 1,000 eggs that go out, and most of them are eaten, and very few live to adulthood. So as their age goes on, there's huge early loss. Okay, not very many of them make it, but the ones that do make it will live relatively long. Your type 2 is kind of a crapshoot. So you have the same chance of dying early as you do later on. Type 1 is late loss. These are your large mammals, your humans, your elephants. So what happens is you have a very low chance of dying early in life, and then as you get older, your chances increase in dying off. Okay, so there become less survivors later, whereas here there are less survivors earlier, if that makes sense. Okay, so this just goes through exactly what I just said. If you need to pause and take a look at it. Here are your 2 survivorship curves: songbirds, annual plants, lizards, many small mammals. And then here's your type 3 survivorship curve. Okay, this is your early mortality, your R selected species. All right, and that's it. I look forward to seeing you in September.